right here. Okay, so we begin chapter 9 and 10 is the science of chemical bonding. Now, to start this, one of the things you kind of have in the back of your mind as a reference is the types of bonds that exist in the universe. There are actually 3 types of bonds. And these are bond forces and hold things together in the material world. There is, of course, chemical bonding, but we have physical bonds. These are interactions between particles having dipole moments or are polarized. They have a positive end of a molecule, negative end of a molecule, and these interact. Water is a good example. It's a dipole. Okay, and if water remains as a liquid because of a dipole interaction called hydrogen bonding. It's not a true chemical bond, but it's strong enough that it converts the H2O into liquid form. Methane, for example, 12, 13, 14, 15, 16 is a gas, but water is a liquid. Okay, it's 18. Small difference between the atomic mass values, but water is always, as you know, liquid, and the simplest organic hydrocarbon, methane, is always a gas at the same conditions at room temperature. These are little bonds that are electrostatic in nature. You can write it down. I guess that means something. Electrostatic dipole interactions is what I was talking about. You have a polar molecule. One end's positive, one end's negative. Well, it, of course, will align itself with the opposite charge. Then there is, of course, chemical bonding. Which is the primary focal point of our work as we get past this, is the joining of elements by either ionic bonding or through a process known as molecular covalent bonding. Chemical bonds are much stronger than physical bonds. Ice is held together in solid form because of the high dipole-dipole interaction. It takes very little energy to break the physical bonds between. Wax is another example that's held together at room temperature in solid form by electrostatic interactions. It doesn't take very much energy to melt wax, but if you wanted to evaporate water, you would have to add quite a bit of energy. Water does not break down. It retains its structure and composition of 2 hydrogens and 1 oxygen. You have to go up to extreme conditions in order to decompose the compounds. So the chemical bonds are quite strong, and we'll learn how to, and we've done a little bit of that when we did molecular bonding. We took the table, and I know you remember that, added up all the bond strengths. I think you remember a little bit of that. We'll do it again. Now, third one is, I know you will appreciate this one, nuclear bonding. These are high energy interactions of nuclear particles. protons, neutrons, and all the little sub-micronuclear particles interact together to hold the nucleus together. With the close proximity of positive protons, you know there's a lot of repulsion. So something's going on that has to overcome that repulsion, and it's quite strong. In Chem 2, we deal with that toward the end of the semester, and it's the last chapter I cover. And we calculate the amount of energy that comes out of a fusion or fission type process. Just for passing, you might be interested in, let's see if I can remember how it works, 3H2, let's see, 3 hydrogens, that's not, let me do it a different way. Hydrogen 3 plus hydrogen 2 goes to helium 4-2 plus a neutron, like that. This is the reaction of the sun. This is nuclear fusion. 1, 3, 2, 1. So 3, this is 1 and 0. So we have a balance of mass and we have a balance of charge. So when hydrogen bumps into one another, hydrogen, tritium, it's called tritium, and deuterium, and this is your helium. And of course a neutron on the end is the outcome plus energy. It's given off that we call sunshine. So you have a, I'm sure, an appreciation of how much of that energy that is. So to deal with nuclear processes is the 10 to the 14 joules and things of that nature. Well, moving right along, our focus will start with physical bonds. We'll talk about with chemical bonds, we'll talk about the physical bonds when we get to the chapter 11 on states of matter and phase change and how phases interact and so forth. Okay. So chemical bonds, by definition, is the combining of elements first by two methods: by electrostatic interaction of ionic particles or overlap, or I'm going to use a different one, or blending of electronic orbitals that share electrons between bonding nuclei. Okay. Now, this implies the existence of two types of bond. One that is electrostatic in nature, and another that is more of a blending or sharing of electrons between two nuclei, and that's exactly what it is. Classification of bonds include, of course, the ionic bonding, some textbooks will call this electrovalent bonding. and is an electrostatic interaction of charged particles again. I'm going to note it. Or ions. The definition of a charged particle in chemistry is an ion, or an ion is a charged particle. And of course, that is the first type. And the second one is, of course, your textbook uses molecular bonding. This is also known as covalent. So some of the terms I'm sure you're familiar with from previous courses, but the molecular bonding results from the interaction of electron orbitals that share electrons between bonding nuclei. Okay, so that kind of sets the stage for some definitions. Move that up where you can everybody see that, all right? And these are bonds which, when formed, result in a dipole moment, positive end, negative end, what this means, within the molecule. Typically, it's represented by what we call a partial positive or partial negative. I'll give you just an idea of this. This is a carbon-chlorine bond. When this one forms, it will have it's like an S with a little circle on the bottom of it, with a negative, and a little circle, S with a circle, with a plus, excuse me, this should be the negative end. This is the electronegative end. This is the positive end. And so when the bond is formed, it has an unequal distribution of electron density between the two nuclei. And as a result, you have charged ends of the molecule in that bond. That is the source of further chemical reactions. In all of chemistry, I used to tell people when teaching this kind of material, chemistry is nothing more than positive looking for negatives all day long. And so if you can find out where the positives and negatives are in a molecule, and we'll show you how to do that before this section ends, then you can pick molecules that have positive, negative ends that will interact and make new molecules for whatever purpose you have. So when we talk about molecular bonding, we're talking about molecular bonds that can be polar in nature. And while I'm at it, you have non-polar covalent bonds. A nonpolar covalent bond would be a bond where there is no dipole. There's an equal distribution of electronic charge around both nuclei. Hydrogen bonded to hydrogen is usually, it shows to be a nonpolar covalent bond because both elements are the same. Both elements overlap and distribute electron charge evenly around both nuclei, and it's referred to as a nonpolar covalent. Ionic bonds are electrostatic interactions between charged particles. Ions formed by electron transfer. In the simplest format of the ionic bond, we find that one of the components of a bond has a positive charge and it results from the loss of electrons, and another component of the bond has a negative charge resulting from the gain of electrons. So if we look at something like sodium chloride, which is very common table salt, in the formation of this, I'm writing it backwards, you have to have an interaction of a cation and an anion. Now, in the formation of the cations and anions, we simply have an element which will go to an ion, a cation, and lose, so to speak, an electron. Transfers an electron to something else. You don't really lose it. And this is, as some of you already know, is an oxidation process. And then, of course, the chlorine, this is chloride when it's in the ionic form, chlorine when it's in the molecular form. So if we took chlorine like that, it would have a tendency to gain an electron and become negatively charged, and this is a reduction process. So the loss of electron is the oxidation, and I'm sure I told you the acronym to remember for oxidation reduction, oil rig. Did I ever mention that? Okay, good. So that helps you kind of keep up with things. Okay, now in the formation of ions, let's do it this way. In the formation of ionic bonds, elements tend to follow the octet rule. You recall from earlier topics this semester, generally the octet rule refers to the gain or loss of electrons by the path of least resistance to achieve a noble gas configuration. So during chemical bonding, elements tend to gain or lose electrons from the valence level by the path of least resistance. To achieve a noble gas configuration. Which of course is the end group on the periodic table. I think everybody's pretty aware of that. Application of the octet rules to the elements on the periodic chart. When we apply this rule to the formation of ions, we look at metals first, and just because they're on the left, we like to list cations before anions. I don't know why. Metals in general tend to lose electrons and acquire a positive charge, and of course that is the cation of the ion pairs, cation, anion. Nonmetals on the right of the periodic chart in general tend to gain electrons and acquire a negative charge, and are referred to as, of course, the anion in there. Now, this gain of loss of electrons by the path of least resistance, we've covered this before, but I'll touch it. Be sure we're on the same page, so to speak. Is lost or gained to achieve the closest, so to speak, closest noble gas configuration. Here we go. Center that up a little bit better. That use up all the room, but I think you understand the idea that we're looking at. Starting here, we want to separate the elements, of course, into the metals and nonmetals, which we're already familiar with right here. And from the staircase plus the rare earth metals, lose electrons and you get a positive charge. That positive charge results from the fact that the number of protons in the nucleus is greater than the number of electrons orbiting the nucleus. So number of protons greater than the number of electrons accounts for that issue. Now, we've been talking about sodium, or the elements in group 1 have one outer shell electron. Elements in group 2 have two outer shell electrons. We jump over the transitions to group 3, and everything in here has three outer shell electrons. Now, as you move down the periodic table, we go from non-metallic tendencies to metallic tendencies. Well, there's only one block, boron, before you hit the metals in group 3. So we throw that into the metal group and say, okay, it also loses electrons. It's a metalloid, so we can get away with it. So sodium, for example, has 3 rings. Okay, you know the row represents the number of rings. Okay, so here we have sodium, and everything in here has 3 rings. So we have nucleus, 1, 2, 3, one outer shell electron. When that one is lost, this remains 2 and 8, and the result is positive 1. If we lose electrons from the valence shell in number 2, this gives us a plus 2 overall. And then 3, we lose the electrons, that becomes plus 3. Now I know this is a review, but I still want to make sure that we're all kind of regenerating the nerves that tell us what this is. Now when we get on the non-metal side, non-metals tend to gain electrons, and that will give them a negative charge. And in essence, the number of electrons this time is greater than the number of protons when that occurs. Now, in the metals, when they lose group 1, 2, and 3, we're not going to talk. I'll bring up the transitions and inner transitions in a minute. When we talk about groups 1 and 2, when they lose their outer shell electrons, like sodium, it will achieve a noble gas configuration to neon. So its outer shell looks like neon's electron configuration. Magnesium, when it loses its outer shell, it also goes to neon. And aluminum has 3 outer shell electrons. It loses it, it goes back to neon. So this is the noble gas configuration that results from that loss of electrons. Now when we talk again about the nonmetals, they tend to gain electrons and achieve the configuration of the noble gas in the same row. For example, carbon is short, has 4 outer shell electrons. Well, octet rule says it can only hold 8 in the outer shell, as you know. Only exception is, of course, hydrogen, which one can go up to 2 in the s orbital. But everything else can go to, main group elements can go to 8. So carbon has 4, needs 4. Okay, so it gains 4 electrons, and that becomes a -4. So does silicon, becoming silane. Nitrogen has 5 outer shell electrons, and so it becomes a -3. So does phosphorus, so does arsenic. Those become -3 elements. Oxygen, -2, sulfur, -2, selenium, and tellurium, all -2s. And then you have the halogens, gain, minus. Of course, they all have the configuration of the noble gas that's in their respective rows and show those charges. Elements are going through the bonding process. Okay, we have to describe them in terms of what we call ionization factors or bonding factors. And what these are refer to the reactivity of the elements. And ionization factors are 3. And I told you this at the end of the last chapter. This is where we will be. A-I-R. A stands for electron affinity, or affinity simply. And electron affinity is how strongly does a given element attract electrons into its outer shell. How strongly or how active are they in adding electrons. This is attraction. You might call it attraction energy. Small radius elements have the valence close to the nucleus, have a high electron affinity. When an electron floats by, sucks it in. If you have a big radius element, electron floats by, all the shells will shield that electron energy, and the electron just slowly adds. We'll get it. The next term is ionization energy. And this is more of a semantic consideration in the scheme that I'm using now. Ionization refers to the loss of electrons exclusively. Now, ionization can be either side in a different context. Ionization, well, it's gaining electrons, becoming a negative ion. Well, that's true. I'm not going to debate that. But in the textbook, it says electron affinity deals with the description of gaining electrons to form anions. And ionization energy deals with the loss of electrons and the loss of electrons and the energy needed to knock those out. Ionization energy, just simply put, loss electrons. And essentially, the nucleus is like a long rope tied to an electron, holding on to that electron. The closer it is to the nucleus, like gravity, the closer we get to the Earth, the stronger that pull, and it takes a lot more energy to knock that electron out. So that's what we're looking at here when we get to that part. The loss of electrons requires a lot of energy depending on where that electron is. And the over-governing factor in all of this is radius. And these are twofold, atomic radius and ionic radius. So when we look at these three terms, they are used to describe the reactivity of elements. So when we talk about ionic bonding, now something just occurred to me on ionic bonding. Of course, implies ionic molecules, ionic compounds, and we learned in early part of the semester that the composition is a metal and non-metal, and then when we get over molecular, everything's going to be non-metal. That's not going to change. Okay, so keep in the back of your mind when we were talking. Don't get lost in the terminology. Like I'm always talking about ionization and this, that, and other. You're still talking about something going on with the metals and something going on with the non-metals. Well, anyway, for forming ionic bonds and ionic compounds, consider the ease of formation of ions. This refers to ease of formation of the ionic compound. So what factors up here applied to an element on the periodic chart would make it easy to form or conducive to forming an ion and then, of course, an ionic compound? Let's go back to our group 1 elements, and we can look at lithium, sodium, potassium. Those are good. Okay, lithium, sodium, potassium. This one has 2 rings. This one has 3. This one has 4. Like that. And all of them have 1 outer shell electron. Like that. Okay? So a moment ago I mentioned that, well, the closer it is to the nucleus, the stronger the pull, the chain stronger, so to speak. So this has a small radius. And of course out here we have a larger radius. So the electron being negatively charged further away from the nucleus. So the bond between the nucleus and what's holding the electron in, okay, is reasonably strong here. Whereas on the other end, when you start getting to the larger ions, francium, you got the electron on the 7th level, somewhere out there in the boonies, you have a very weak nuclear electron interaction as you go down the chart. Well, the way that is couched in this issue is we have how much energy do you need to put into that electron to knock it out, versus how much energy you need to knock the sodium out, like last valence electron, and so forth, like that. So, in a qualitative, strictly descriptive format, knowing only that, well, the closer it is, the stronger it's held on there. To knock this electron out, we have to have higher energy than we would have to have for knocking out the potassium outer shell electron. So we say the higher energy applies to the electrons close to the nucleus. Whereas when you get farther away from the nucleus, this is kind of an intuitive thing once you think about it. Yeah, in other words, you already, oh yeah, I knew that anyway. Lower energy needed with larger radius. Now, that's the intuitive aspect of why these one's easier to knock off than the other. We have a weak attraction, you have lower energy, okay? And so we couch these in terms of these three issues up here. We say that the electron, while it's in this orbital, is associated with a high electron affinity. A high ionization energy. And that relates to a small atomic radius. So you see how the radius, the ionization energies, and electron affinities are used now to describe, well, what can you tell me about the ease of forming this ion? Well, being a metal, you know it's going to lose electrons, so we apply it to that concept, apply it to losing the electron. On the other side of this, with the large radius, the nuclear interaction with the electron is a low electron affinity. And since it has a tendency to lose electrons, and it has a low electron affinity, there's a weak attraction. It would have a low ionization energy. Okay, and the relationship to the radius is inverse in this context, large atomic radius. So if you were trying to choose between lithium and potassium as far as making an ionic compound, for whatever reason, and you choose the one that forms the cation the easiest, of course it'd be potassium because of these reaction factors, element reaction factors. Now we got to hook it up with something, all right? So that's the other side of the consideration when we apply these reaction factors to the elements. And of course, let's look at the halogens now and see what the issue is. And what I've drawn here is just the halogen series and representatives of some orbitals, and 1 and 2 orbitals in the fluoride. Chloride has 3, and all of them have 7 outer shell electrons. And so their tendency in each case would be to gain an electron to achieve the anion that we need for making the ionic bond for whatever reason. Now, the factors that will certainly affect this, if it gains an electron, this of course goes to F minus 1, chloride minus 1, bromide minus 1, and iodide minus 1. Now, let's just go back and apply the reactivity factors of elements. What can we say about the potential for forming the ion? Well, first of all, we want to apply reaction factors relative to gaining electrons. Ease of gaining electrons. And we're talking about radius, ionization energy, and electron affinity. Those three. So we want to take each one at a time. So, and when we consider the trend, what can we say about radius and the gaining of electrons? Okay, if it's closer, if the outer shell or the valence shell is close to the nucleus, remember what I say, it's a strong attraction. So radius, small radius, produces strong attraction for valence electrons. Okay? So if it's a strong attraction, that translates to ionization of the valence electrons. Ionization energy to remove valence electrons. So when we're talking about gaining one electron, actually we have two options in the octet rule. You can gain one electron to achieve a noble gas configuration, or lose 7 to achieve the noble gas configuration. So when you look at that, path of least resistance would certainly be to gain an electron, because of the attraction the nucleus has for the electron cloud. It being closer, it's smaller, blah, 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 so forth and so on. So how could we couch this comment here? Ionization energy to remove valence electrons is very high. So if you wanted to remove 7 electrons, you're going to have to use tons of energy, right? So I mean, that would make sense. But to gain 1 electron, it'll fall in its orbital very easily. You won't have to give up very much. It'll give it up, but it will be easier to gain than less. So what you say here on ionization, remove valence electrons, very high ionization energy. And put parentheses out there, not favored, because the electrons are held on much, much, much tighter. Okay, so this is kind of a natural selection kind of issue. Let me move it up some so you can see what I'm talking about. So when we have ionization energy that's very high, that says not favored if you can't read my scribble. So anyway, so now the last term is electron affinity. Actually, electron affinity is an energy number, and we'll show you that in due time. It's the amount of energy released when an electron is added to the valence shell, kind of like a ball falling into a hole. Okay, and if you look at it from that context, I'll show you kind of an analogy here. And if you had a ball and you dropped it same time, identical ball into the holes, the energy lost is whatever this depth is, and the energy lost in case 1, let's call it case 2, delta E lost certainly is a lot higher. So this one applies to a strong attraction, and something that has a small hole to drop ball into is a weak attraction. And so the way we couch this in terms of gaining electrons in the outer shell, and using this terminology, we say that small radius, okay, strong attraction for valence electrons, has a high electron affinity. Because of small radius and strong nuclear attraction. So that would be the case 1. Okay? So as you go further out, you get on to bromine and iodine that are 6 and 7 shells out there. Well, they will take on an electron just like everybody else in the group. But when it adds the electron, it doesn't give up much energy. It's very weak attraction. So it's very easy to remove if it comes in. So the weak attractions apply to a low electron affinity. Okay, which is a result of large radius and poor nuclear attraction. So what I'm going through and what we're going through together here and talking about these topics is, first we have to see what the reactivity of the element is and put it in a form that it's ready to bond in. We've written equations on the board and we'll call them standard state equations. But when you mix those compounds and substances together and shake them up in a bottle, you won't get what's on the right side of the arrow because they're not in the right form to bond. And that's where the next topic is. When we talk about ionization energy, what we're essentially meaning is the amount of energy needed to remove an electron from its valence orbital. Now I want you to understand that's a lot of energy compared to what the electron, other energies the electron has. We talked about the Bohr model of the atom in which you had n equal 1, then we went to n equal 2 and n equal 3 and on up to n equal 7. And I said, okay, electrons can jump out by absorbing energy. And they go up to, say, a level, and then they fall back down to whatever and give off this energy when they fall back down. You see them as bright line spectral. Well, electrons do that. But electrons can absorb enough energy that they leave and go out to infinity and leave the presence of the atom totally. And that's the concept of ionization energy. We add enough energy in here to knock the electron completely away from the element. Now, when we have an element, something like, we'll go with, I don't know, gas sodium's fine. I'm gonna do magnesium. Okay, change that, sorry. Okay, we're taking magnesium. Well, the neutral element has 2 electrons in the outer shell, and then it has 8 electrons, and this is only a partial, of course, and then it has 2 in the center. Terminology-wise, when we talk about the amount of energy needed to knock the first electron out, that's associated with what we call the first ionization energy. Okay? Now Now watch me close on this so you'll understand. And it's logical. It's very easy to understand. So what's happened here is magnesium now only has 1 electron and then 8 electrons inside and 2 electrons. And it still has 12 protons. Didn't change. So the 12 plus charges here still has 12 plus charges here. However, 8, 9, 10, it only has 11 negative charges. Okay? So what that essentially means is that the nucleus of magnesium is holding on to that electron. So when we look at this, at the beginning, at the neutral element, we've got the nucleus holding on to 2 electrons. So it's splitting its holding power between 2 electrons. Okay? So that's the first ionization energy. But since this is stronger hold than it was when you had the other electron in it, the second ionization energy is greater than the first ionization energy. Matter of fact, the first ionization energy for magnesium is 738 kilojoules per mole. But to knock the second electron out, it's 1,451 kilojoules per mole for that second one. Okay, so we knocked that second electron out. And so we now have a magnesium, still has 12 protons here, 2, 8, and no outer shell now. Remember, the outer shell is your valence. But the inner shells, the N equal 1, N equal 2 in this case, is your core structure. Essentially, it's stable. It resists any changing. You can easily remove valence electrons in ionization. But once you get rid of that valence, this next level in is first ring of the core structure. Is not going to be able to ionize that. It will take an incredible amount. And I'll just take a couple. Say we're looking at these 3. And this would be the 3rd, 4th, and 5th ionization energies, for example. Delta EI is what I should be using. That third, well, I only have 2 of them. I've got the next 2. I don't have the 5th one. The third ionization energy, to knock that one out, is 7,733 kilojoules per mole. Compare that to 1,400, okay? So 4 or 5 times larger. When you remove that one, the next one is still held on even stronger, and the ionization energy is 10,540 kilojoules. So the idea of preparing an element for bonding in that has to be, you have to take into account how much energy am I going to need to make it bond. Well, elements in the first column, talking about the reactivity of elements in group 1, exclude hydrogen for the moment, talk about the metals. 1 outer shell electron is easier to remove than 2 outer shell electrons. So this would be low delta EI here. This would be a slightly higher delta EI. Low delta EI is very reactive. This is poorly. That says poorly reactive. So preparing the element for bonding is very important that you take into account or understand as a chemist that the element, the position and location and interaction with the nucleus governs the reactivity of that element. Magnesium, for example. We played with some of that in the earlier part of the semester. Well, you take a piece of magnesium, hold it in your hand, or drop it in water, and it just kind of lays there, not very reactive at all. You put sodium in your hand, it'd probably burn a hole in it. That's how reactive sodium is. There's some videos. I think I may have put one up on people that throw big bags of sodium out in a lake, and you can see it's just incredible. It about clears the lake. But you throw a piece of magnesium, it goes to the bottom and lays there forever. And so that's the idea about pairing and getting the metals ready to bond, or the non-metals ready to bond. Of other elements here. I think we're going, yeah. Okay, what this is, I get something to point with. These are valence in the gold. These are your valence energies. For example, sodium, and you can see 496. Can you see that, I hope? 496. Once the outer shell is lost, you can see how fast the energies increase. First, this is second energy, third, fourth. Magnesium we just talked about. Aluminum has 3 valence electrons. Well, that's still, when you get a third one, it's kind of high. But the inner shell, 11,577. So here's the first ionization energy of sodium, 496, then 45, 62, 69, 12, 95, 43. So the closer you get to the nucleus and more electrons you pull off, the more energy it takes to remove. And ionic radii at the same time. If we go in series, the atomic radius decreases with increasing atomic number. That is, if you were going left to right on periodic chart, you'd see, say, sodium would be a pretty large circle. Then you'd have, next one would be magnesium. Go into aluminum, silicon, phosphorus, smaller, sulfur, smaller, chloride, chlorine, smaller, and you'd have the smallest one in the atomic row would be argon, like that. Now the reason for the trend is as you move left to right in this series, you are increasing atomic number. Which of course is the number of protons in the nucleus, where if you go left to right on the periodic chart. At the same time, also increasing numbers of electrons that are orbiting the nucleus. So as you increase the positives, you're increasing the negatives, and so the multiple of increases combine to give you a greater attractive force between the nucleus and the electron cloud, and the radius begins to decrease across the series. And that's true for the main group elements. Transition metals typically retain a common radius. Now here's one I pulled off the internet, you can see the size of the atoms as they trend to the end of a given series here. But when you look at the transitions across here and the intertransitions, they're pretty uniform in their size. Now keep in mind the intertransitions are still metals and would tend to lose electrons. And there's one little footnote that you need to keep in mind about the transitions losing electrons. When writing out the electron configuration for, say, zinc, its core is argon, and we have a 4s2 and a 3d10 right there. That's the outbound order. Now, if you want to just keep the valence shell on the outside, we'll just say both of these are correct as we've written. As we write it here, both of these are used, and the reason the 4s is put on the end is just a convenience factor to identify where the valence shell is, and that's the highest quantum number. Well, when zinc undergoes ionization, zinc goes to zinc plus 2, meaning losing a couple of electrons are lost. So this outer shell is lost. How many electrons remain? It ain't 8, it's 10. When the transitions and intertransitions do this, and it's common, those are referred to as pseudo-noble configurations. So that's more of a, well, this is how that works, and that's it. Okay, we won't see very much of that beyond this. Now, also, even though we're incomplete at a d orbital, and I just throw this is not found until way over in the back of the book. Some people, I don't know why they put it back there. But if you take something like, I don't know, iron, it's 1, 2, 3, 4, 5, 6, a 3d6. So it's a iron, argon, 3d6. Let me put it by the alphabet. That's what I want to do. 4s2 is full, and then we got a 3d6. That's the alphabet order right there. Now, when this undergoes ionization, the rule, and it can be confirmed, electrons always come out of the valence shell first, because these transitions can acquire several oxidation states. +1, +2, some of them jump up +6. So some of the electrons in the D structure are removed. And you have to understand the next chapter 10, geometry and how they rearrange themselves to understand why the D orbital loses electrons. And we'll get to that in time. But ionization of transition metals and intertransitions begin at valence level. So if any of the elements in the transition or intertransitions are involved in ionic bonding, the first electrons that are removed or will remove by natural selection process will be the valence electrons, the highest principal quantum number.
So the valence in this one, it was 4s2, and if that's lost, it becomes a +2 ion, like that, and it retains a pseudonoble configuration after the electrons are lost. Okay, one more here. Atomic radii in groups. In general, atomic in groups increase with increasing atomic number. Because additional energy levels are simply added. So in the simplest format, we go from hydrogen, it has one ring, lithium, 2, and then to sodium, 3, potassium, 4, and so forth. Rubidium, 5, cesium, 6, francium, 7. So the radius is increasing with increasing atomic number. Like that. How does that affect the reactivity of the element? Well, the group 1 in this particular case all have one outer shell electron. So what can you say about ionization energy trends from top to bottom? Well, the electron is very close to the nucleus in hydrogen, so it would be from top to bottom, we'd have a high delta E ionization here because the shells are closer to the nucleus. And as you move down, we have a low delta E I's toward the, get further. It doesn't take as much energy because there's not much attraction between nucleus and valence. So we have a decreasing ionization energy with increasing radius. And as you go down, well, group 1 typically loses electrons. It's not going to gain 7 to achieve a noble gas configuration. So what can we say about electron affinity? It doesn't exist. It has almost no affinity to add electrons. And you can theoretically figure out, well, you can put an electron in, it loses this kind of energy and stuff like that, but it's just pointless because none do gain electrons and achieve negative status in the context of what's going on here in our ionic structures. Bonding. In forming any chemical bond, whether it is ionic or covalent, formation of chemical bonds is exothermic. That is all of it. Doesn't matter whether it's molecular or ionic. Breaking chemical bonds is endothermic. Simple as that. And the relationship between these two is that the amount of energy lost in formation equals the amount of energy needed to break it. So delta E for formation is equal to delta E for breaking. if we gave up 1,000 kilojoules in formation of a bond, and you want to break it, you're going to have to put that same 1,000 back in to pull it apart. That's all it means. In considering ionic bonding, we use a flow chart kind of issue and describe how each component is formed on the way to forming an ionic compound. An ionic compound is formed from ions, so we got to make ions out of whatever the constituent elements are. But when you start an analysis, you start with the standard state equation. If we're going to analyze the energy changes in the formation of sodium chloride, you use, and it has a name to it, it's called the Born-Haber cycle. And we have one for covalent bonding, just like this idea. It doesn't have a name. Call it whatever you want. It contains 6 primary reactions and 6 types or terms associated with energy, 6 different energy types. Okay? So we're going to start with sodium chloride. And the standard state equation is sodium. Then you look at it in the book and it's 0, delta HF. Plus, we'll go half mole of chlorine gas. That's the standard form of chlorine. Right there. And that will go to sodium chloride. That's a solid. That's called the standard state equation. If you took metallic sodium, put it in a bottle, and some chlorine gas, put it in a bottle, shook it up, you would not get anything. This is a standard state equation. In order to make an ionic compound, you've got to convert these standard state elements or constituents of the sodium chloride into ions. So we go through a little kind of a flow chart here like this. Well, all ions, remember this, starting here with a standard state, we're going to convert them to a form we can convert that form into ions. Well, ions are formed from gas phase. This is solid phase. So before we do anything, what we'll do is convert this sodium into sodium in the gas phase, like evaporation. Going from solid to, well, not evaporation, sublimation. That's a sublimation reaction. So that's going to be an endothermic process, and I will show you in a minute what the numbers are. Then, once you get into gas phase, then you will add the energy and kick out the electron and make the sodium ion in the gas phase. Okay, that's one pathway. Sublimation and then ionization energy. Chlorine, this is in a bonded form. So we have to promote this out of that bonded form by putting in enough energy to break the bond. And that's called half of the bond energy, whatever chlorine is, Cl2. And when we go from here, the energy is 0 here in the standard state. You remember delta HF is 0 for a basic element standard state. But when you put it into the gas phase, 1/2 mole of Cl2 is just 1 Cl2. So we have Cl in the gas phase. Okay? That's going to have a higher energy than what it is in the standard state. Sodium gas is going to have a higher energy than it has in the standard state. And I'll show you the numbers in a minute. Now we're ready to gain our electrons. And here I should have put loss of electron. Negative electron means loss of electron, okay? And when we do, we get Cl minus. It's in the gas phase. Now these are ready to bond. So sodium chases down chlorine because the opposites attract. And we form a bond, ionic bond. It is sodium chloride. And that change in energy right here is a delta HX. And delta HX is called the crystal lattice energy. And the objective of the problems that you can see on exam day is calculate delta HX. That's what we're going to go through right now. So delta H, calculate delta HX for forming NaCl solid using the Born-Haber cycle. Okay, and delta HX is defined as the crystal lattice energy. And we'll talk more about properties of solids when we get over in chapter 11 on states of matter and stuff like that. Okay, so each one of these pathways is an individual reaction, and the algebraic sum of all of the pathways equals what the energy is for the standard state. So let me try to, I'm going to put these in color so you can hopefully see it better. Maybe this will come out all right. This first energy change up here is standard heat of formation that you'd look up in the textbook. So delta HF is the first energy change that we've got to work with, and that's the standard heat of formation. So where do you get that? You look in the book, in the back of the book, and you find each one of these are 0. Remember, basic standard state element 0. But sodium chloride in the back of the book has a specific value. And that value is negative 411 kilojoules per mole. Okay, that's the standard state, standard heat of formation. You could take either one of these as the next one. This is number 1 you would have to take into account. You take number 2 into account, either one. I'm going to choose sodium. Well, going from solid to a gas, that'd be delta H of atomization, delta HA, heat of atomization. That's going from solid to gas. That's all it is, sublimation. Is another term like that. Now, at ground state, basic standard state here, sodium is 0. So we'll have 0 kilojoules right there. But when you look in the book, you find sodium in the gas phase is 107 plus kilojoules. So when we get it in here, we've added 107 kilojoules per mole. So we've gone from here to here. Hess's law. Products are the gas, reactants of the sodium, 107 minus 0, so the delta H of atomization here is 107 kilojoules. So that's the change between those two. Okay, the next one is also, this is bond breaking, and you can call it atomization if you want. So this is also a delta HA for chlorine. I'm going to do it like this, and this is the delta HA for sodium, if you want to do it like that. Okay, well, the value for chlorine is 0 kilojoules. But when you promote the chlorine into gas phase, you have to add 121 kilojoules of energy. So when we get here into this state, it's 121 kilojoules plus, because we had to heat it to get it up there. And this one too. You put a plus on there just to emphasize that you've added energy, endothermic, in that step. And chlorine's 121. Okay, 121 right there. So now we've got them in gas phase. Now they're ready to ionize. Now, one of the things you got to understand in the ionization calculation is products minus reactants. Hess's law thing. You're starting here and you're going to products. This is reactant side, 107. You're starting at 107, and then you're going to put some energy in and knock the electron out. So the way you figure this is you look in the book and the table and get the energy value for sodium plus gas phase. And that turns out to be sodium plus 1 in gas phase is 609 plus. 609 kilojoules plus. So this one is now 609 kilojoules per mole, and that's a plus. I'm just going to emphasize that right there. Therefore, the ionization energy, delta H ionization, is the product energy minus the reactant energy value. So that is 609 minus a plus 107 kilojoules. So that says 502, and a little scribble right there in the middle. 502. That's the difference between the end and the beginning. That's Hess's law calculation. And we do the same thing for ionization. Now this is going to gain an electron. Anytime electrons gain, energy is liberated. So that process is exothermic through here. This is endothermic to knock an electron out. So, you know, see the plus we put in here like that. So we need to look up Cl minus. We're already at 121 right here. So we need to look up Cl minus in the gas phase. So we look back in our table. Chlorine minus gas, a minus 234. A minus 234. So the chlorine is a minus 234 kilojoules per mole. We're going from 121 to a minus 234. So its product minus 234 minus a plus 121. So you subtract both of them. The difference is a minus 234 minus a plus, okay, which turns that into a minus. And so we ultimately go minus 121. Did y'all catch what I just did? I'm trying to save space here. So it's minus 234 minus a plus 121, so that makes them both minus. And then we add those together. A minus 355 kilojoules exothermic for that reaction right there. We've got crystal lattice energy is the bonding energy. That's what we're going for right now. I'll show you in just a second. The delta HF is the standard heat of formation. That's this first reaction. Heat of atomization, which is the sublimation of sodium. Then we have heat, delta H atomization for the chlorine. That's heat of atomization. And you can look at that as bond breaking if you wanted to. The ionization energies, sodium, delta H I for sodium, loss of electron. So it's going to be exothermic when we lost that. No, it's endothermic. Loss of electron is what that says. Endothermic. Loss of electrons, endothermic. I could put delta H greater than 0 for that. I hate to lose it on the page. I'm going to move it up. I'll move it back here in a second because I need to. Delta H ionization for chlorine is an electron affinity energy, is what they call it. But it gives up so much energy, so this is ionization energy, so to speak, or electron affinity energy. It's a number, and is no, that's a gain of energy. To getting tired. I'm sorry, correct that on the sodium. It's a gain of energy by the electron knocked out. Electron affinity is a loss of energy. A loss of gain of damn, I'm going so fast I can't even think. That is a loss of electron and gain of energy. This is a gain of electron and a loss of energy. Just put it in here. Delta H less than 0. How about that? Okay, so we got 1, 2, 3, 4, 5. This last one is, of course, the crystal lattice reaction, delta HX, which is your bonding energy, ionic bonding energy. Okay, so I'm trying to define everything and show you where everything is and context of this thing. The sum of all the energy changes below the blue line equal the energy change above the blue line. So the equation that we have that we use to solve the problem, have y'all followed me? Any questions about up to this point? How I got each of the numbers and each of the reactions? We all good? Let me know now. Okay, there is some Born-Haber cycle worksheets online that use different compounds. Please do work them so you don't miss this one on the exam. Anyway, we have the delta H of formation, standard heat of formation, is equal to the algebraic sum of all the other energy. So we've got a delta H of atomization for sodium plus delta H of atomization for chlorine plus the delta H of ionization for sodium plus the delta H affinity, I'm going to go AFF, for chlorine gaining an electron plus delta HX, which is your bonding energy. The amount of energy liberated when plus touches minus, like that. So substituting the numbers in here, we have a minus 411 kilojoules right there. This one is a plus 107 kilojoules here, plus a minus 3, that's 121. Plus 121, sorry, kilojoules, plus the sodium ionization, 502 kilojoules, plus the affinity minus 355 kilojoules, and solve for delta HX. Right there. Everybody following kind of what I'm doing? Once you get here and see the idea of how to put the equation together, it's really just add and subtract things. So the biggest issue is, does everybody understand how I got the numbers for each transition in the diagram? Once you get that and understand that how to set the equation up, really add and subtract from there. So crystal lattice energy now for the sodium chloride bond. So that's the ionic bonding energy for our problem that we're trying to work is minus 411, minus 107, minus 121, minus 502, plus 355. Yeah. And everybody's going to come out in kilojoules. I want to check it before I published it to the world, how stupid I am. Okay, so anyway, please, for goodness sakes, go through one of these. If you struggle with the meaning of whatever energy number is in this collection, please let me know. Okay, and I'll help you work your way through it.